Welcome to lesson 29 of industrial instrumentation. In this lesson, we will consider, we will cover the optoelectronic sensor 2, and basically the contents will like this, that we will first cover the basics of fiber optics and then some basics of fiber optics, because we have already discussed some basics in the industrial in the lesson 28. We will cover details the transmissions of light in the optical fiber. Then I will come to the fiber optic based sensors. Let us look at the lesson. So, optoelectronic sensor 2 contains introduction to fiber optics, travelling of light through the cable, then monomode cable, multimode gradient index cable, and fiber optic sensors. These are the basic things which we will cover. At the end of the lesson, now please one thing you note that in this particular lesson sometimes I will tell the cable, but cable means basically I want to mention that it is a basically fiber optical fiber, nothing other than that, right. So, at the end of the lesson the viewer will know how does the light travel in the optical fiber, fiber optic switches, intrinsic fiber optic sensors, extrinsic fiber optic sensors, right. Now, you see this is a typical a fiber optics. You can look at lights are, I mean, how the light travels in optical fiber. This is basically we have shown a step index fiber. So, in the step index fiber you see here, please note that I am using the British English. So, it will be fiber like this one, or I can take the other pen. So, it is fiber, and when the light travels, it always goes through a total internal reflections. You see here light is traveling and there is a incidence is such a way that it will have a total internal reflection. So, that none of the lights will be lost in the cladding, and totally it will be reflected. So, that refractive index of this one of the core, this is a core, this is actually the core, and this is the cladding, right, these are the cladding. So, the diffractive index of the core is higher than that of the cladding, and incident lights we actually arrange to and fall in such a way, so that the light will get a total internal reflection. So, it will follow a zigzag fashion. Please note it will be like this one. So, it is not like this, it will be like this, light will follow like this one. So, this phi should be greater than the critical angle of incidence, because if it is not more than critical angle, so there will be no total internal reflection. So, we have to arrange for the total internal reflection, so that even if this fiber is not straight, if it is bent like this one, so light can travel through this. That is the idea of this, I mean, optical fiber. So, even though we know the light travels on a only straight line, using these total internal reflections, we can see that in the optical fibers light can go through a bent path, right. That is a tremendous advantage, and using that principles we have used many sensors. Though if it is a bend like this, you will find that there is a loss of intensity and all those things. Okay, if the light travels straight, so loss of intensity will be, even though we are saying that it has a total internal reflection, all those things will be, some light will be dispersed. Okay. So, using that principle we will find that we made several sensors, right. We will come to that later on. Now, let us come to the basic, the principle how the light travels in a optical fiber. Transmission of light ray. The light ray shown in figure 1, this is just the previous figure, known as the meridional ray, as it passes through the axis of the fiber core. Okay. If it goes to the fiber cores, we will call meridional ray. This type of ray is the simplest to describe and is generally used when illustrating the fundamental transmission properties of the optical fibers. This is always we use these fundamental transmission properties of the optical fiber. Acceptance angle look like this. You see what is the acceptance angle, what is the numerical aperture. These are the basic definitions of the optical fiber, which we will discuss in this particular lessons at the beginning of this lesson. Now, the geometry concerned with the launching a light ray into an optical fiber is shown in figure 2, which illustrates a meridional ray A at the critical angle phi within the fiber at the core cladding interface, right. So, it is, you see that here, if you look at what is this is a figure 2, you see it is a conical half angle, this is the phi theta A. So, theta is the, I mean, because we must know what is the maximum value of theta is allowed because this face, if this is the face of the fiber, this face should be highly polished. If I fall the light in the normal directions, okay, that is okay, but that is not always possible, especially in the case of if you use a light source as a LED, light emitting diode, there will be in different angle light can fall. So, I have to, we must find what is the maximum angle value of theta A, so that when light enters the core, okay, there is a total internal reflections, right. So, that we must find it. Okay, light you see traveling like this one, and some lights are traveling like this one, having the total internal reflections. This light you see, this is a more than the acceptance angle. So, this light will not get the total internal reflections, it will be reflected within the core and it is lost. Okay. So, this is lost, I mean this will not be transmitted through the core, this will be lost in the cladding itself. Whereas, if I can make within this theta, angle of incidence is within theta A, we will find that we will get a total internal reflections within the core of the fiber. Okay. So, we must find what is that. Let us go back again. Now, the geometry concerns with the launching a light into the into an optical fiber is shown in figure 2, which we have shown, which illustrates the meridional ray A at the critical angle theta c within the fiber at the core cladding interface. It may be observed that this ray enters the fiber core at an angle theta A to the fiber axis and is refracted at the AR core interface before transmission to the core cladding interface at the critical angle, right. So, we have chosen theta in such a way, so that it will be refracted in the AR core, because when it is launched in the air, I mean when launched from the transmitter, we are assuming that it is for some distance the light will travel in air, then it is coming to the core. So, when it is in the core, it is refracted and it bends towards the axis, right. So, that bend towards the axis of the core. So, that the and that bends will be in such a way that will be more than the, so that when the light falls in the core cladding junction, so it will be more than the critical angle of these two mediums. So, that we will get the total internal reflections. Let us look at. So, this is the things at which I talked about. You see, this is a angle, this is a ray, and this is a maximum angle. If we go beyond that, I won't get any total. This we have shown here. So, you see it is more than theta A. So, light is falling, another light is falling. So, it is not, it is refracted, there is no doubt about this, because here the medium refractive index here, this one of the core is higher than that of the cladding. So, it will be because if it is a normal, so it will go away from the normal, and I will get a total, I will get a bending like this one, right, because there is a jacket outside. So, the light will not go. So, it will be the cladding, it will be lost, right, that I told you earlier also. Now, hence any rays which are incident into the fiber core at an angle greater than theta A will be transmitted to the core cladding interface at an angle less than phi c and will not be total internally reflected. So, there will be no total internal reflections, as I told you, and theta A is sometimes referred to as a maximum angle or total acceptance angle of the fiber optics. It is a total acceptance, you know, it is a solid cone, right. It is not a, two dimensions, it is a solid cone, theta is basically a solid cone. If the fiber has a regular cross section, that is the core cladding interfaces are parallel, there are no discontinuities, and incident meridional ray at the greater than the critical angle will be continue to be reflected and will be transmitted through the fiber. That is very good. Now, what is the numerical aperture? Numerical aperture is very, it is a specifications of the fiber. So, you must know what is the numerical aperture. So, we will calculate here the numerical aperture for a optical fiber. You see figure 3 shows a light ray incident on the fiber core at an angle theta 1 to the fiber axis, which is less than theta A acceptance angle for the fiber, because you see the rays to be transmitted through total internal reflections. So, incident ray might be, should be always less than the acceptance angle. If it is more, then it will not be total internally reflected, right. So, it should be less than the acceptance angle for the fiber theta A. What is figure 3? Let us look at. This is our figure C. This is theta 1, the acceptance angle is slightly higher. Okay, acceptance angle will be like this one, right. Okay, this is our theta A. Right. So, it is less than that. So, I getting a bending, because it is a higher refractive index. So, light will bend because this is the normal to the plane of the surface. Okay. So, it will bend like this one, this is theta 2, then it will go like this one. Clear? Let us go back again. Okay. The ray path for the meridional ray, so launch into the optical fiber in air at an input angle less than the acceptance angle for the fiber. Assuming that the entrance phase at the fiber core to be normal to the axis, then considering the diffractions at the air core interface and using Snell's law, we are writing NO into sin theta 1 equal to N1 into sin theta 2, right. So, this is N1, this is NO, this is the refractive index of air and this is the refractive index of the core, and this is the angle of incidence of theta 1 and this is the angle of diffraction theta 2. So, that we can easily write the Snell's law N0 sin theta 1 equal to N1 sin theta 2. Okay, this is equation number 1, where we can see here if the phi is greater than the critical angle at the core cladding interface. Okay, if the phi is, I mean, hence equation 1 becomes, if we write that the, you see if the sin theta 2, again if we can go here. Now, this is if you take this one, so this is you see this is 90 degree. So, obviously, this is theta 2. So, obviously, phi will be basically 90 degree minus theta 2. So, if it is that, so obviously, I can write that where phi is greater than the critical angle at the core cladding interface, if it is phi is greater than the critical angle of the, otherwise there will be no total angle reflections. I can write N0 sin theta 1, N1 it will be actually sine of pi by 2 minus phi, because if you take that angle as a right angle triangle, but where here this is a right angle triangle, ABC is a right angle triangle. So, obviously, I can write quite obviously that N0 sin theta 1 equal to N1 into cos phi, right, or N0 sin theta 1, so N1 1 minus sin square phi to the power half. We can write this equation number 3. Again for the core cladding we can write again, you see for the core cladding interface N1 sin phi equal to N2. Why? If you look at, you see when the light will be deflected here, okay, because this is N1 sin theta 2, okay, N1 sin theta 2 equal to N2. Here you see here whenever it is deflected, so it will use a phi. So, obviously, if I apply the total internal reflection principles, I can immediately write that expression. So, what is that? Again for the core cladding we can write N1 sin phi into N2, is not it, because that will be 90 degrees. So, obviously, it will be 90. So, where phi is the critical angle of incidence of light from the core cladding, because in that case if it is critical angle, if phi is the critical angle, this will be sin N2 into sin 90 degrees. So, sin 90 degrees is equal to 1. So, obviously, it will be N1 sin phi equal to N2, where phi is the critical angle of incidence light from the core to cladding. So, which I can write sin theta A equal to N1 square minus N2 square. What is N1 square? I put N1 inside. So, it will be a square N1 square, and we have here we have N1 square into sin square phi, that is equal to N2 square. So, okay, so to the power half. So, fine. Equation 4, apart from the relating the acceptance angle, you see this is actually this n theta A we are calling the acceptance angle, right. How to find the acceptance? That is the reason we made it sin theta N2 equal to sin phi equal to 1, otherwise we cannot do it. Equation 4, apart from the relating the acceptance angle to the refractive indices, serves as the basis for the definitions of the important optical fiber parameter, which is called the numerical aperture. Hence, the numerical aperture or NA can be defined as NA equal to N naught sin theta A, theta is the acceptance angle, equal to N1 square minus N2 square to the power half, equation number 5, where theta A is the acceptance angle of the fiber. I should actually write the theta in the previous equation, equation number 4. Since the NA is often used with the fiber in air, so NO is actually unity, because the refractive index of the air is taken as unity. So, it is simply equal to sin theta A. So, it may also be noted that the incident meridional rays over the range of theta, theta 1 is the incident angle. So, it should be lie between 0 and theta. If it is 0, so there is no question of total internal lift, light will straight will flow, will pass through the 5 core. But if it is more than 0 degree, so obviously more than 0, obviously there will be total internal reflection, because it is less than theta. We have chosen theta in such a way, so that it will be any light within this range, if it falls, it will go through a total internal reflections. So, the light will be propagated within the fiber. The numerical aperture may also be given in the terms of the relative refractive index difference delta between the core and the cladding, which is defined as delta equal to n1 square minus n2 square by 2 n1 square. So, which we can write n1 minus n2 by n1 for delta. If it is delta less than 1, we can write like this one, equation number 6. Hence, combine equation 5 and equation 6, we can write that numerical aperture equal to n1 2 delta to the power half, which is equation number 7. The relationship given in equation 5 and 7 for the numerical apertures are a very useful measure of the light collecting ability of a fiber, okay, because we must know, accordingly we will make our transmitter. Even though, I mean, the fiber optic sensors also we need transmitters, okay, we need receivers. Though we talked about as if we are only using for communication, that is not actually true. You will find here also the light will travel through the fiber. They are independent of the fiber core diameter and will hold for diameters as small as 8 micron. Even if it is the diameter of the core is 8 micron, the light will, I mean, these equations will follow. While the attenuation has been minimized, there is a remaining problem in that the transmission time of the parts of the beam that travel in the zigzag manner will be greater than the light which enters the fiber at 90 degree to the face, and so travels in a straight line to the other end. Okay. So, obviously, if it falls on a 90 degree, is not it, if the light falls on a 90 degree, because we are talking about so much, you see, if I take a dark one. So, we are talking about like this one. This is our fiber and we have a cladding here. So, this is our central. So, light is falling like this one, right, but at the same time light may fall the straight line. If it falls in straight line, so the angle of incidence is 90 degree, is not it? It is not very good. I can take this one. Okay, this is 90 degree then, is not it? It does not matter, because it is even in that case, even it falling on perpendicular to the face, but the angle of incidence theta a in that case will be 0 degree, is not it? Theta should be always less than that value, otherwise there will be no total internal reflections. Anyway, let us go back. While the attenuation has been minimized, there is a remaining problem in that the transmission time of the parts of the beam that travel in the zigzag manner will be greater than the light which enters the fiber at 90 degree. Quite obviously, a light traveling in a zigzag fashions with a total internal reflection, it will have some time, where the light, when the light, I mean, travels straight away through the fibers, okay, when the light falls with the theta equal to 0 degree, obviously in that case it will take less time, is not it? In practice, the incident light rays to the cable will be spread over the range given by the acceptance angle, and so the transmission times of the separate parts of the beam will be distributed over a corresponding range, right. It will be distributed transmission time of the different ray. So, in the case of multimode fiber, so this is very predominant. These differential delay characteristics of the light beams are known as the modal dispersions in an optical fiber. So, it is the dispersions of light. So, lights are getting more and time, it is not equal time that it reaches at the end, but this problem can be eliminated in the case of graded index fibers. So, because these problems what we talk about is a multimode fiber, multimode step index fibers, this will be more, you will find it easy to see this one in the graded index fibers, right. It will not, probably not be there, these modal dispersions will be almost eliminated in the case of graded index fiber. Now, step index fiber, the optical fiber with a core of constant refractive index N1 and a cladding of slightly lower refractive index N2 is known as the step index fiber, as simple as that. It is because the refractive index profile for this type of fiber makes a step change at the core cladding interface. Clear? So, let us look at that type of step index fiber or step index fiber. So, the step index fiber can be two type, it can be monomode, can be multimode. So, let us look at first monomode, let us take a white page. So, it will look like this. You see that I have a, I can take a large dark pen. The cladding here. Okay, I have a fiber here. Okay, let me draw the engineering second and the center line which we studied in the first year in the drawing, like this one, right. So, what will happen, you see here, this is the cladding, both side cladding, and center we have is a cylindrical in shape. What will happen in the case of multimode fiber? So, light will travel in these various directions. So, it will travel like this, then it will travel like this, right, it will like this one. It can also travel like this, it can travel like this, it can travel, or it can go like fashion, it can go in a more like this, right, in all these different cases. Now, the index profile, that means the refractive index profile will look like this one. It will have a step change, that means you see it will look like here so actually it will look like this one, right. So, this will right. So, let me get back the pen again, pencil. So, it will look like this, right. So, here the refractive index here is N1 and here the refractive index is N2, right. So, this is the refractive index we are plotting, Ri, refractive index we are plotting. So, this is a multimode fiber. So, this is core, this is cladding. This is multimode fiber, okay. And in the case of step, this is a please note there is a step change of the refractive index Ri. Is not it? There is a step change here at this point. There is a step change. That is the reason we are calling it step change multimode fiber, right. We have a step and we have a single mode fiber also, right. So, it looks like this. So, I have a core as before, then I have so in the case of multimode fiber, sorry, in the single mode fiber, the core diameter is extremely small. So, that is the problem, we need different sort of sources here, okay, and directional sources. So, the light will travel, in this case the refractive index profile, if I plot the refractive index Ri, it will look like I have a small change here, so this is our N1, this is our N2, okay. So, this is our central line. So, the light also travels through this one, okay, like this one. This is core and this is cladding as before. This I talked about the single mode fiber, single mode step index fiber. These are we call again the step, there is step index, okay, there is a step change of the refractive index. So, index means basically we are talking of the refractive index, please note. So, there is a step change of the refractive index, that is the reason we are calling it single mode step index fiber, okay, because there is only one mode light can transmit through the core. Core diameter is usually very small, right. Let us go back. So, this is about the step index fiber, clear. So, the optical fiber with a core of constant refractive index N1 and a cladding of slightly lower refractive index N2 is known as a stepped index. It is because the refractive index profile for this type of fiber makes a step change at the core cladding interface. Now, a multimode step index fiber with a core diameter of around 50 micrometers or greater, that is larger enough to allow the propagation of many modes, okay, in many incident situations, many modes within the fiber core. It means that there are many possible ray paths to the fiber. Multimode is basically there is a different ray paths or multiple ray paths to the fiber, that is we are calling multimode. However, monomode step index fiber allows the propagation of only one transverse electromagnetic mode, and hence the core diameter must be of the order of 2 to 10 micron or micrometer, right. So, it is quite small, we have seen that. Okay, if you find the graded index, it is in between the two, right. Let us we will come to that. Now, comparison of the two modes of fiber. If I compare the two modes, the monomode step index fiber has a distinct advantage of low modal dispersions, as I told you earlier, which is basically defined as the broadening of transmitted light pulses since only one mode is transmitted, whereas with the multimode step index fiber considerable dispersion may occur due to the differing group velocities, as we told you, because there is a light ray which is going straight to the along the axis, that is one speed, and what is going through a total internal reflections, okay, because there is large incident ray, so that will have different group velocities. So, that at the end there is a modal dispersions, right. When the bandwidth requirement is low, the multimode fiber has a several advantage. Now, again the problem is that in the case of multimode fiber, obviously the bandwidth will be narrower, right, has several advantage. Now, what are the advantage? If I look at the advantage, that you will find that in the case of multimode fiber, we do not have any restrictions on the transmitter, because we have to transmit light, either you have to use a LED or light emitting diode or laser sources. Since the light emitting diode has a little dispersed, the ray will be dispersed, so that can be used for transmissions of lights in the case. So, we do not need any very stringent requirements of the coherent sources and all those things, which is necessary in the case of single mode fiber. So, this is a great advantage, because the cost of the transmitter will be reduced, even though for the low. So, therefore, if the bandwidth requirement is low, obviously we go for a multimode fiber, because what will happen that I can save the money on the actually the on the transmitters, whereas in the case of single mode fiber we cannot use LED light emitting diodes, we have to use the laser sources, which is very coherent and all those things, right. Now, graded index multimode fiber, the graded index fiber do not have a constant refractive index, there is no step change of the refractive index in the fiber, but a decreasing core refractive index with a radial distance from a maximum value of N1 at the fiber axis to a constant value of N2 beyond the core radius in the cladding, right. So, there is a step change, so you will find there is some tremendous advantage. So, far the modal dispersion is concerned, we will get. So, we are getting the advantage of the gradient index fiber, you see that we can use the same light sources, but we can use the here LED, but the bandwidths will be slightly better. Because here what advantage is that the light will reach at the end, even whether it is going in a straight to the core or through total internal reflections in different angles, it does not matter, light will reach the end of the fiber at the same time. So, this is a great advantage. So, a multimode graded index fiber has a parabolic refractive index profile. So, let us look at that, what is that actually talking about. Let us take a white page, it will look like this. That means, you see the refractive index profile will look like this. We have is a multimode fiber. So, it has it's look like this, it is going like this. This is N2, and this refractive index N1. But please note this N1 I should not write here, actually there is a okay. So, actually what will happen, you see that N1 is at the center point. N1 actually if I look at, so it will, the refractive index N1 is at the center point here actually. So, the refractive index will slowly decrease to the N2 value as I go from the center to the cladding, because this is a cladding and this is the core. So, at the center the refractive index is N1. As I move towards the cladding, the refractive index slowly changes, slowly decreases at the at the point N2, it is at the point these core junctions, it is now N2, right. So, that is now the refractive index profile, if I plot, it will look like this one, no more step change. So, it will look like this. So, I have, so it is parabolic like this one, right. So, this is our N1 at the center. So, I can erase again. So, I can, so sorry, okay. Here it is N1 and here is it is actually this will be like this one, this is N2, right. So, this is, so light will travel like this one, you see light will fall and it will travel like bent path like this one, because slowly light will bend, right. That is the reason we are calling it. Right. So, light will come like this one. It is not necessary that it is to be go to the cladding, it is not necessary, because before the incident angles between the layer, because there are multiple layers. So, it will move like this one, clear. This is the difference. So, this is core, this is cladding, clear. That means, if I draw, it will looks like this one. That means, if I draw, if I have a fiber like this one, okay. So, the light will fall, this is our axis. So, I have a several layers. So, okay, suppose this is N1, this is N2. Now, ultimately it is coming to the cladding. So, this is our cladding, okay. So, light will fall like this, it will bend again to this one, this will bend again, okay, until it gets the total internal reflections, clear. So, this is some, I mean I can write N1, N2, N3, N4, right. So, N1 is greater than N2, greater than N3, greater than N4. This I mean for visualizations or understanding the what is the how the gradient index fiber works, this is the way we are discussing. So, it is not necessarily all the rays will go at the core cladding interface. In between it may have a total internal reflection if the incidence angle is more than the critical angle, clear. So, multimode gradient index fiber has a parabolic refractive index profile. The gradual decreases in the refractive index from the center of the core to the cladding creates many diffractions. Advantage, what are the advantage? The multimode gradient index fibers exhibit for the less modal dispersion than the multimode step index fiber. Reasons I will tell you. Although many different modes exist, the different group velocities of the modes tend to be normalized by the refractive index gradient, because of the refractive index, because you see the light which is travel at the center and along the axis of the fiber core will have a lower speed, okay. So, if it goes to the extreme, I mean core cladding interface, it has a higher speed, because the refractive, as you know, if the refractive index increases, the speed of light also decreases. The rays traveling close to the fiber axis, that what I told you, have shorter paths when they compared with the rays which is travel into the outer regions of the core. This path is shorter, but the speed will be lower. So, ultimately the I mean the time at the same time it will reach. So, the modal dispersion is not be there, right. However, the near axial rays are transmitted through a region of higher refractive index and therefore travel with lower velocity than the more extreme rays it compensates for the shorter path lengths and the reduce the dispersions of the fiber, which is going at the end, which has a less it will take less time, because even though it is getting total internal reflection, but the refractive index is less. So, the speed of light will be higher those cases. The multimode graded index fibers with the parabolic refractive index profile, which I have shown, have transmission bandwidth may be the order of magnitude greater than the multimode step index fiber bandwidth. So, this is a great advantage of this one. Now, let us come to the fiber optic sensors. Now, there are basis of the operation of the fiber optic sensors is a translation of physical quantity measured into a change in one or more parameters of a light beam. The light parameters that can be modulated are one or more of the following: intensity will be modulated, phase can be modulated, polarization will be there, wavelength can be modulated, and transmission time can be modulated. So, in most of the cases we will find the intensity of light is very easy to modulate. Okay, some senses we will discuss where the intensity of light is modulated. Fiber optic sensors usually incorporate either glass or plastic cables, because now all plastic cables are coming up very fast. Glass is cheaper than the silica based fiber. So, we must give some emphasis on the all plastic fiber cables, because it is a loss is more though in the case of all plastic cables, but it is cheap. Also its mechanical strength is better than the all glass fiber. All glass types are rarely used because of their fragility, and plastic cables have particular advantage for the sensor application because they are cheap and have a relative large diameter 0.5 to 1 millimeter, making connection to the transmitter and receiver easy. Using multimode there is no problem. So, the connection transmitter and the receiver transmitter to the cable to the fiber optic cable, also from the cable to the receiver is easier. You know, in the case of monomode fiber, it is most difficult to launch light, to couple a transmitter and the light itself, because it is a small diameter, due to small diameter, that is a nuisance. Okay. Whereas, in the case of plastic cables, we can have a larger diameter. So, the launching of light is easier. So, that type of headache will not be there. The cost of the fiber optic cables itself is insignificant for sending the applications, for sensing the applications, as the total cost of the sensor is dominated by the cost of the transmitter and receiver. So, always prefer light emitting diode and photodiode which are to be used as a transmitter and receiver respectively. Fiber optic sensors typically has a long life. For example, the life expectancy of reflective fiber optic switches is quoted as 10 million operations. Their accuracy is also good, with for instance plus minus 1% of full scale reading being quoted as a typical inaccuracy level for fiber optic pressure sensors. Further advantages are the simplicity, low cost, smaller size, and high reliability and capability of working in many kinds of hostile environments. Hostile environments, where there is a dust, okay, when there is a chance of a large electromagnetic field where the electrical connection is very hazardous. You cannot use electrical taking, suppose I have a thermocouples and there is it is going through a transformer where it is large magnetic field, so it will influence, because if there is a surge or something in the transformer, that will affect our reading. So, right, and if you look at the strip chart recorder which is recording the temperature, that also will create problem. So, that type of problem does not come in the optical fibers. Okay, that is a great advantage of this type of device. Moreover, please note, in many process industry, this is it is forbidden to use a high voltage, especially the electrical cables. The voltage should be around 40 volts, especially in the hydrocarbon industry, which is highly inflammable industry. With that type of applications, the fiber optic sensors, though previously people are using the pneumatic systems, okay, where the safety is very high, but pneumatic system has it is rugged, it is rugged obviously, but it is very large in size. All those things, the problems are there, maintenance is difficult, whereas if you use a fiber optic sensor in that type of situations, which will satisfy both the things, that means which is safety will be there, because since it is a very low voltage and entire transmission is through the light, there is no electrical connections as though, right. However, in spite of these obvious merits, industrial uses is currently quite low, that is we must admit, right, even though this is quite high, because there is some vicious circle. That means the people, those who are using the conventional sensors with the pneumatic sensors, these were not new. When the we are using pneumatic sensors in process industry, pneumatic systems in the process industry. When the electrical system came, which is now converting all 3 to 15 psi of control signal to 4 to 20 milliampere, there is also long objections. But later on we slowly we found over the decades all these pneumatic system were replaced by the electrical systems, like where the current is 4 to 20 milliampere. Similarly, we also hope that in future this all will be replaced by the fiber optic sensors. Now, fiber optic sensors, let us look at two major classes of fiber optic sensors exist. What is the intrinsic sensors and extrinsic sensors? In intrinsic sensors, the fiber optic cable itself is the sensor, whereas in the extrinsic sensor, fiber optic cable is only used to guide the light to and from the conventional sensors, right. So, that is not actually censored as such. I mean, I am talking about the extrinsic sensors, but we are using actually the extrinsic sensor, that cable, to take out some light actually to the conventional sensors, which is might be far away, right. We will see some that typical situation. One of the example is measuring the jet engine exhaust temperatures. Okay, I can use a optical pyrometer, but it is very difficult online measurements, right, because jet engines, jets is running at an altitude of 40,000 feet, and its online measurement is difficult. So, I have to install optical fiber which will send the light to the transmitter. At the receiving end, I can use one optical pyrometer, might be disappearing filament type, to measure the engine temperature, because thermocouple will not work, because the temperature is extremely high. Now, intrinsic sensors can modulate the intensity, phase, polarization, wavelength, or transit time of the light, right. This one. Sensors which modulate light intensity tend to use mainly multimode fibers, but only the monomode cables are used to modulate other light parameters. A particular features of intrinsic fiber optic sensor is that it can, if required, provide distributed sensing over the distance up to 1 meter. Light intensity is the simplest parameter to manipulate in intrinsic sensor, because only a simple source and detector are required, right. The various forms of switches shown in figures 4 to 6 are perhaps the simplest form of this, as the light path is simply blocked and unblocked as the switch changes position, right, changes state. Let us look at modulation of the intensity of light of the transmitted light takes place in various simple forms of proximity, displacement, pressure, pH, and smoke sensors, and some of these are sketched in figure 7 to 9. Let us look at. In proximity and displacement sensors, the latter are often given to the special name photonic sensors, and the amount of reflected light varies with the distance between the fiber ends and the boundary. Okay. In pressure sensors, the refractive index of the fiber and hence the intensity of light transmitted varies according to the mechanical deformations of the fibers caused by the pressure. We will show some example. This is, you see, a simple shutter switch. That means, if the shutter comes down, obviously we will find, okay, if the shutter comes down like this one, what will happen? You see that it will modulate the light, because if the light is coming, intensity, it will not get any. So, this is a shutter switch. This is a reflective switch. If the switches changes positions, okay, suppose if the switches changes position like this one, then what will happen? If the switches position, if the switches come to this position, so obviously the light sources, or the light, if you switches like position, light source will not get any light, light out. So, at the receiver we won't get any light. So, this is a reflective switch. This is also can be used for the as a switch for the fiber optic sensors. Okay. This is the fiber optic switches. That means, it is optical micro switch. That means, if the fiber bends like this one, the fiber bends in this direction. So, obviously, if the light, I have a light source, I have a light receiver. So, obviously, I will not get a light output. So, this is all uses my optical micro switch, right. So, this is also a example of fiber optic switches. This is, you see, the applied force we are using, which, as we say, the some sensors is force measurements. What will happen if the light falls on this one? Okay, this straight light fiber, this is the fiber. Okay. So, this will be corrugated in shape, is not it? If it is in corrugated in shape, so the obviously light intensity will be modulated by looking. So, if the more and more pressure, it will be more and more corrugated. So, the intensity light here which will receive, because if it is straight, obviously I will get more light. So, if it is bends like this one, it will get less light. So, obviously, the sensing the intensity of light can be calibrated in terms of force, right. This is the example intensity modulated sensor roller chain pressure sensors. You see that if the chain pressure is higher, then what will happen? This if the roller chain pressure is higher and higher, this is the same example if whatever the pressure force sensors we have discussed, the more and more bending of the light beam here. Okay. So, obviously, I will less light will receive at the will be at the end. So, that can be calibrated in terms of the pressure. So, how much is the chain pressure can be calculated by looking at the intensity of light receiving at the receiving end. You see this is some with this intensity modulators proximity sensors. If the light goes, if the light is coming through this one and is getting reflected and it is light is coming out. If it is coming more and more, so if you have a reflecting surface here, so obviously I will receive more and more light. Okay. If it is far away, so I will get less light. So, the intensity of light again here is modulated according to the position of the these proximity sensors, right. Here it is the pH sensors, which will be the principles will be explained after some time. In the pH probe, the amount of light reflected back into the fibers depends on the pH dependent color of the chemical indicators in the solution around the probe tip, right. What we are launching and what we are receiving, obviously the intensity will not be same. Finally, in the form of smoke detectors, two fiber optic cables placed either side of a space detect any reductions in the intensity of light transmission between them caused by the presence of smoke. Very simple. Suppose I have a I have a light source here, and sorry, let me take. So, okay, I have a fiber here and I have a fiber here. So, I am getting a if the smoke comes here, what will happen? The intensity of light received at this end, this is the transmitter and this is our receiver. So, what will happen? Intensity of light will be decreased, since the smoke will obviously decrease the intensity of light. So, obviously this can be used as a smoke detector. So, it will turn on some alarm or some annunciation, right. Now, a simple form of accelerometer can be made by placing a mass subject to the accelerations on a multimode fiber. The force exerted by the mass on the fiber causes a change in the intensity of light transmitted, and thus allowing the acceleration to be determined, and the typical accuracy quoted for this device is plus minus 0.02 g in the measurement range of plus minus 5 g. It is extremely good, I should say, and plus minus 2% in the measurement range of up to 100 g. A similar principle is used to probes which measure the internal diameter of the tubes. The probe consists of 8 strain gauge cantilever beam which track changes in diameter, giving a measurements of resolutions of 20 micron, right. So, in many situations we need this term. A slightly more complicated method of affecting light intensity modulation is the variable shutter sensor shown in 10, and it consists of 2 fixed fibers with 2 collimating lenses and a variable shutter between. Okay. It looks like this, you see. What will happen? You see that this movement I can get from many places. I can get from the pressure sensors, I can get from the Bourdeau tube. We have already discussed the Bourdeau tube, I will discuss that in some details. Light is falling in, I have a collimator lens. So, if I can put the shutter here, what basically at the outputs also will be less, right. Because if you use a collimator lens, obviously there will be no dispersions of light from the at that light end. So, that I can use a simple light emitting diode in the multimode fibers, right, for that as a transmitter. You see why I am saying this shutter can be used. You see that suppose I have you have studied the Bourdeau tube. See, tips looks like this, is not it. So, if the pressure increases, we have seen that this tip moves like this one. Okay. This with some arrangements we have connected to the needle, okay, or pointer, and that dial is calibrated in terms of pressure. Here you see this movement I can put on a shutter, is not it. So, light is coming in and light is coming out with the collimator lens and all these things whatever we have. Okay. So, light is coming parallelly like this one, it is then again it is coming to there, right. Then what will happen if it moves? So, the this shutter will move inside, shutter will move inside this, I should draw like this one. That means, if the tip moves, that means if the shutter will go inside. So, it will the intensity of light will modulate it. So, if it is goes entire end, so I should say that it is reached the large scale. So, this intensity of light also will be varied according to the pressure which is giving inside the Bourdeau C tube. So, that can be calibrated in terms of pressure, right. Now, movement of the shutter changes the intensity of light transmitted between the fibers. This is used to measure the displacement of various devices, as I told you, Bourdeau tubes. Bourdeau tubes, actually we know that we have basically a tip movement is with some sector and pinion and all those things, you will find it is converted to a circular movements on a scale. And we can use it for diaphragms also for the bimetallic thermometer, same principle. Diaphragm, what will happen, we know that very easily. Now we have a diaphragm. So, if the pressure in diaphragm, stretched diaphragm, it looks like this. Okay. So, if its pressure increases, it moves like this one. So, if I now include a shutter here, and again lights will come here, lights are coming out, light in, light out, then what will happen, the shutters position of the shutter will give you the will modulate the intensity of light. So, this intensity of light can be calibrated in terms of pressures, because here I am giving the pressure. So, diaphragm will bend like this one, is not it. Also, in the case of bimetallic strip, as you know, the bimetallic strip, what will happen, which is used for the measurement of temperature, also for it can be switched. If the temperature increases because of the two different alpha 1, suppose this alpha 2, that means the different coefficient of expansion. So, it bends like this one, right. So, now if this tip is moved connected to a shutter, so obviously what will happen, you will find that this will be modulated, right. So, this is the one other way of doing that thing. So, yet another type of intrinsic sensor uses cable where the core and the cladding have similar refractive indexes, but different temperature coefficients. This is used as a temperature sensor. Temperature rises causes the refractive indexes to be even closer together and losses from the core to increase, because if the refractive index is almost same, there will be more and more loss to the cladding, there will be no total internal reflections. So, thus reducing the quantity of light transmitted at the which will be received at the receiving end. Refractive index variation is also used in the form of intrinsic sensor used for cryonic leak detection. The fiber used for this has a cladding whose refractive index becomes greater than that of the core when it is cooled to cryogenic temperature. The fiber optic cable is laid in the location where cryogenic leaks might occur, and if any leaks do occur, light travelling in the core is transferred to the cladding where it is attenuated. Cryogenic leakage is thus indicated by monitoring the light transmission characteristics of the fiber. Another use of the refractive index variation is found in the devices which detect in the oil in water. In many cases, it is necessary to detect. So, that case, what is the principle you see? This uses a special form of cable where the cladding is sensitive to oil. Any oil presence diffuses into the cladding. So, oil will be diffused in the cladding and change the refractive indexes of the cladding. So, obviously, light again will be if the refractive index changes. So, it will change the transmission of light, because the light will, because in the multimode fiber obviously there will be total internal reflection. So, that will prevent the total internal reflections. So, at the receiving end whatever the light will receive, that will have a less intensity, right. Unclad fibers are used in a similar way. In this, any oil present settles on the core and allows the light to escape, right. So, that is another thing. The extrinsic sensors, okay, thank you. Extrinsic sensors, extrinsic fiber optic sensors use a fiber optic cable, normally a multimode one, to transmit the modulated light from the conventional sensors. Okay, as I told you, just to give an examples that the in measurement of temperatures of a jet engine, exhaust of the jet engine, where we can use an optical pyrometer, but the light is to be transmitted to the optical. That is type of sensors we are calling it extrinsic sensors instead of intrinsic sensors. So, it is not fiber optic as a sensor as such, but the transmissions of the light from the in optical mode to the conventional sensors. A major feature of the example sensors which makes them so useful is their ability to reach places which are otherwise inaccessible. As I told you, a jet engine which is traveling at a height of 40,000 feet and it is inaccessible. So, it is in that case optical fiber is very suitable. One example of this is the insertion of fiber optic cables into the engine of aircraft to measure temperature by the transmitting light into an optical pyrometers located remotely from the engine. Extrinsic fibers optic sensors provide excellent protections of measurement signals against noise corruption. So, that is inherent to the any optical fiber sensors, it is immune to the electrical noise, surge, anything, it does not matter. And moreover, two optical fiber can go side by side without having any crosstalk, which is not possible in the electrical fiber. If I take the thermocouple lead wires, two thermocouple lead wires goes parallelly, then if there is a surge in one, that will affect the other thermocouple lead wires also. So, obviously that will affect the output which you will receive. Unfortunately, the output of many forms of conventional sensor is not in the form which can be transmitted by a fiber optic cable. Conversion into the electrical form must therefore take place prior to transmission. For example, in the case of platinum resistance thermometer, temperature changes are translated into unbalanced voltage of a Wheatstone bridge, right. The unbalanced voltage is modulated and launched in the fiber optic cable to the usual type of transmit, because unbalanced voltage unbalanced voltage also will always give the measurement of temperature, but that can be modulated, that can be converted through a that voltage, unbalanced voltage we can give to a LED, accordingly it will give the light intensity. So, the intensity of light will be modulated, will be dependent on the unbalanced voltage. So, obviously the intensity of light will be measure of the temperature of the object in which we put the RTD. This complicates the measurement process and means that the low voltage power cables must be routed with the fiber optic cable to the transducer. One particular adverse effect of this is the advantage of intrinsic safety is lost, because we are using the electrical system. So, that intrinsic safety which we talked about so much of the optical fiber, that is lost there. Now, fiber optic instrumentation networks looks like this, that little or any savings arise of the installing the fiber optic links in instrumentation networks. Indeed, they may be cost penalty, because many sensors we are using. However, there are great advantage in terms of the links immunity to corruptions of the signal carried. Immunity to current surges caused by the stray electromagnetic fields also affords protection to the computers in the network, as such can cause the software corruptions. As with the fiber optic sensor, the cost of the short fiber optic links in instrumentation networks is dominated by the cost of the terminating transducer. That is a problem, that means everywhere I need a transmitter and receiver, that limits the use of that, increasing the cost. But in some applications, as I told you, safety is most important. So, in that type of situation we should not consider for the cost, right. However, as the length of the fiber link becomes greater, the cost of the fiber optic cable becomes more significant. The cheapness of the plastic cables is attractive for instrumentation network, but they cannot be generally be used because it has a large loss, as I told you, there is a large signal attenuations in the plastic cable, but in the short range it is very useful, because that will reduce the cost of the fiber. Though, as I told you repeatedly, the cost of the fiber is insignificant compared to the cost of the transmitter and the receiver. One disadvantage of the fiber optic compared with electrical conductors in network is that the light connections at the ends of the cables are much more costly than the electrical connections, and branching of the light through the cables is not is difficult to implement. What is that? You see, it is very simple. What it looks like this. I have electrical circuits like this one, okay. I can have branch it, I can make another branch, I can make another branch, or I can make another branch like this one, okay. I can do like this one, I can put like all the different branches in possible, but in the optical fiber it is very difficult. If I need branching, I need another transmitter there, okay. So, the bend of light is not possible, okay, which is very easy in the case of optical in the electrical system. The current research is focused on the distributed sensors measuring different process variables along a fiber optic cable. Alternately, sensors of the same type which are located at various points along a cable are investigated as a means of distributed sensing of a single measured variable. Okay, that is only possible, but it is coming out. The fiber optic sensors are coming out very fast. When we think that within few decades, I think within the next decade, the fiber optic sensors will dominate. It will replace all the electrical sensors or electrical transmission systems in the instrumentation networks in any process industry. With this, I come to the end of the lesson 29 of industrial instrumentation.